right, so as Andrea said, I will present my work on automating the collimator alignment using machine learning. This was the topic of my PhD, so it wouldn't have been possible without the supervision and guidance of Gianluca, Belen, Stefano, and Adrian. Okay, so I'll start with an introduction. The Large Hadron Collider is 27 kilometers long with over 1,200 superconducting dipole magnets. It accelerates and collides two counter-rotating beams at 6.5 tera-electron volts and stores energies higher than 300 megajoules. And for the upcoming LHC, we expect to store double this energy. As a result, the magnets and other sensitive equipment must be protected from any damage that may be caused. We have various protection systems in place, one of which is the Collimation System. So in the LHC, we have around 100 collimators, and we add more collimators over the years. In fact, right now, during the long shutdown too, we have 8 new slots, which will be filled with collimators. So this is a very complex system, and this requires a fast setup. Now, each collimator has 2 jaws, and these jaws are aligned with a tight gap of less than 3 millimeters between the jaws in order to concentrate the beam losses into the warm locations. Collimators are vital for machine protection and for the optimization of detector background. So although we need to set them up as efficiently as possible, we also need to be precise. And the jaws are moved with a precision of 5 micrometers. So here we have a diagram of all the collimators around the LHC. We have in blue, we have beam 1, and the collimators assigned to beam 1 are also in blue, and in red we have beam 2. We can see here the 4 different experiments, and we have most of the collimators in IR7 to enhance betatron cleaning, and we have a few as well in IR3 to enhance momentum cleaning. Now, this is a collimator. We can see it's made up of 2 jaws, a left jaw and a right jaw, and the jaws are placed on either side of the beam axis. We can move each of the jaw corners of the collimator individually for when we want to align collimators at different angles. Now, this is a diagram of the collimation hierarchy. Basically, we have different families of collimators, and here we can see that we have the primary collimators that are positioned closest to the beam. Slightly further out from the primary collimators, we have the secondary collimators to absorb the showers that come from the primary collimators. And then slightly further retracted, we have the tertiary collimators. We also have absorbers and dump protection collimators. Now, it is important to note that at each collimator position, the beam center and the beam size is different. So this is why we need to align the collimators towards the beam to be able to determine the beam center and the beam size. And one last thing about the collimators is that they are positioned to clean in 3 planes. We have collimators to clean the horizontal plane, others to clean the vertical plane, and others in the skew. Now, in order to prepare the machine cycle at the start of each year, we go through a commissioning phase. Now, this involves aligning the collimators at the different machine states. So at injection, we align 75 collimators plus 4 injection protection collimators. At flat top, we align the same 75 collimators. During the squeeze, we align 16 tertiary collimators. And in collisions, we align the same 16 tertiary collimators and 12 physics debris collimators. Now, these numbers are the collimators we aligned in 2018. Of course, as we add more collimators, and then these numbers will change. So to align the collimators, we have 2 types of beam instrumentation available. The first is the beam position monitor. And here we can see that these are BPM buttons that are installed in the collimator jaws directly. And these were introduced during the long shutdown before 2015 to 20% of the Collimation System. And these are able to align the collimators knowing the position of the beam. The other type of instrumentation used to align collimators are the beam loss monitors. And these are placed outside the LHC cryostat, so these are external to the collimators. And basically, these work by recording the beam losses generated by collimators as they touch the beam. So, for example, here we have an example of a collimator, and its left jaw is touching the beam. And here we can see the showers are picked up by the beam loss monitor further downstream. Now, this process of moving a collimator jaw towards the beam and then observing the signals in the beam loss monitor is repeated to align a collimator using what we call the beam-based alignment. Now, aligning collimators with beam position monitors is straightforward and it's very fast. So what I will discuss today during the presentation is the beam-based alignment and how to speed this part up for the remaining 80% of the collimators that use this. So let's move to the beam-based alignment. So as I mentioned, here we have the beam and we select a collimator to align, and this has its respective beam loss monitor. Now, here we have an example of the losses we would see in a beam loss monitor when the collimator is far away from the beam. We can see that the losses are pretty steady, and based on this, we select a threshold slightly higher than the losses. Now, once we do this, we select the jaw that we want to move. So let's take, for example, this jaw, and it starts moving towards the beam. Once it touches the beam and the showers are picked up by the beam loss monitor, we can see here that the losses exceeded the threshold. Once this happens, the collimator will stop moving, and we will analyze these losses to determine whether a collimator is aligned or not. If we are happy and the collimator is aligned, we move on and repeat the same procedure to the next jaw with the next jaw. Now, when we align a collimator, we also align the reference collimator, and this is usually taken to be the primary collimator of the plane. And the reason we align the reference collimator is to form a reference cut in the beam halo. And once we do this alignment, we can then calculate the beam center from the final collimator position and the beam size using the reference collimator aligned before and after. So to give an overview of the beam-based alignment, we select the collimator, and if we first move both the jaws simultaneously towards the beam. We keep moving it until it actually touches the beam. And once it touches the beam, we can start by aligning the left jaw. Once this has touched the beam, we move on to align the right jaw. Now, when the right jaw touches the beam for the first time, we go back to realign the left jaw. So then we go back to realign the right jaw, and then once we're happy and this touched the beam a second time, we will classify this collimator as aligned. So this is the process to align a single collimator. Now, I mentioned before that we also need to align a reference collimator. And the way this works is we align the primary collimator of the plane, and then once this is aligned, we align the collimator itself. We go back to aligning the primary collimator, and at this point, we can save the settings of the two collimators. Now, when I say aligned, so to align here the primary collimator, it's this whole procedure I just mentioned here, and likewise, when you align the collimator here, it's again the same procedure. Now, since 2011, this beam-based alignment was semi-automated. Now, what does this involve? The user must first select the collimator. The user must then select a BLM threshold to stop the jaw from moving, as I explained earlier. And once this is done, the collimator will automatically move towards the beam, and then it will automatically stop when the losses have exceeded the threshold. Once this is done, the user must once again step in to determine whether a collimator is aligned or not. Now, of course, this is very time-consuming for a large number of collimators, and also we would require a good number of collimation experts to monitor and control this alignment. So since 2018, I fully automated the automatic alignment, and this does not require any human intervention. And the key underlying factor for this is the use of machine learning to determine whether a collimator is aligned or not. So let's have a look at the problem of the collimator alignment. So basically, here we have two examples of BLM signals. In both cases, the losses have exceeded the threshold. However, there is a clear difference between these two when a collimation expert would look at them. In the first case, we have an alignment spike, which indicates that the collimator jaw has touched the beam. Now, we can tell with the quick rise in the losses here and the slow decay in the losses. This, for us, indicates that we have an alignment spike. Whereas here, these are non-alignment spikes. These basically were not generated by the collimator touching a beam, and they're caused by other factors in the LHC, for example, beam instabilities or crosstalk from other collimators. So basically, this indicates that we need to resume the alignment of the collimator. And okay, so in order to distinguish between these two, we need a more advanced algorithm, and this is where I applied supervised machine learning for binary classification. So why supervised machine learning? Essentially, this is a task-driven approach whereby it learns to map the input sample onto the target variable. So the task here would be to align the collimators, and alignment campaigns are very repetitive, so it's a perfect example for machine learning. In this case, the input sample would be the collimator position and the BNN signal, and the target variable would be the spike class to determine whether the collimator is aligned or not by automatically classifying whether we have an alignment spike or a non-alignment spike. So here we have a few examples of alignment spikes in green and non-alignment spikes in red. We can see they have various shapes and sizes. And what I did was I collected a data set of around 8,700 samples like this from alignment campaigns in 2016 and in 2018. And using this data set, I trained 6 machine learning models for spike classification and to compare them together. So these models are the logistic regression, neural network, support vector machine, decision tree, random forest, and gradient boost. And essentially, the idea was to pre-train these models so that they can then be used in real time for collimator alignment. And in 2018, I used the majority vote of these 6 machine learning models. So at the point in time when we want to align the collimators, the data that we have, as I said, is the 100 Hz BNN signal and the 1 Hz draw position. Now I need to be able to quantify this to give it to the machine learning to train on. So what I did was I engineered a number of features. So the first thing is to quantify the rise in the losses, the quick rise in the losses. And I chose to use either the spike height, the maximum value, and the maximum value as a function of the steady state before the spike. These are 3 different ways that I can use to sort of quantify this value here. Likewise, and then I try to quantify the spike decay, and this can be done using either an exponential or a power or a Gaussian function. The final feature is the draw position sigma to have it relative to the rest of the collimators. So given all of these features, the first thing that I needed to do was analyze the importance of these features and try to find which features do I actually need. So the first thing I did was that I tried to search for a correlation between the features. So here in cyan, I highlighted the features that describe the quick rise in the losses. In green, I'm highlighting the features that describe the slow decay of the spike. And over here, the magenta, I'm highlighting the features that have a strong correlation with the spike class. So here we have the features correlated with each other to try and understand a bit more about the features. The next thing I did was I used 5 machine learning models. I gave them all of these features, and I asked them to order the features based on how much information the features can provide. So the feature that's given the first position is the most informative feature, and the feature that's given the last position is the least informative feature. And in this bar plot here, I summed the position each feature was given by the machine learning model. So essentially here we have the most important informative feature, and here we have the least informative feature. And the last thing I did was I applied sequential forward feature selection for each of the 6 machine learning models that I mentioned earlier. Here, for example, we have the support vector machine. And essentially what this does is I give it a number of features, and it starts picking the features one by one based on how important they are, and it discards the rest. So basically, this was a long analysis just to sort of understand the different features that I had engineered. And bottom line is that I ended up selecting the spike height, the exponential function for the spike decay, and the drop position in sigma. Now, using these features, I then created the data set, and I split the data set into 85% for training, using 10-fold cross-validation randomly stratified 30 times, and I held out 15% of the data set for testing. The performance metric I use for fine-tuning the machine learning models is precision, and the reason for this is because it enforces no false positives. Now, why is this important for us? So basically, a false positive is when the machine learning model tells us that the collimator has touched the beam and it is aligned, when in fact it didn't. And this is not okay for us, because this means that we will move on to the next collimator when this collimator is not yet aligned. So we will end up with a collimator that is not aligned. Whereas a false negative is when the machine learning model classifies the collimator as not yet aligned when it actually did. This is perfectly fine for us, because in this case, we simply move the collimator closer to the beam until eventually the machine learning detects this as aligned. So at the end of the day, with a false negative, we will still align the collimators, whereas with false positives, we end up with a non-aligned collimator. So this is why I use precision. Now here I am showing the precision obtained using the data set on the testing data set, as I mentioned before, using each of the models. And we can see that all of the models achieved over 90% precision, with the support vector machine having a slightly higher precision than the rest. And it is important to note that there is no need to train these machine learning models unless there's a significant change in the BLM signal or in the collimator position or in the data source, basically. Now, whenever I present this and say that, for example, the machine learning models are able to have a 90% precision, I'm saying 90% just for this example, the first question I'm always asked is, what happens to the remaining 10% of the collimators? Are they misaligned? Now, so I prepared this slide to sort of explain this a bit. So if we have 100 collimators, each collimator, we want to align first, we need to align first both jaws, and then we align the left jaw, and then we align the right jaw, like I explained before. Now, when we align both jaws, we first have a number of non-alignment spikes until eventually we have the one alignment spike that we need. And then we move on to aligning the left and right jaws. And again, in these cases, we have a number of non-alignment spikes for the left jaw, a number of non-alignment spikes for the right jaws. And in these cases, since we realign these jaws twice, we need 2 spikes per jaw. So this is the number of classifications we would need to align a collimator. Now, if let's say for this example, we take each of the non-alignments per both left and right to be 2, this would result in 1,100 classifications for the 300 jaw alignments required to align the 100 collimators. So when I say that the machine learning models are obtain a precision of 90%, I'm not referring to the fact that 10% of the collimators are misaligned, but I'm saying that 10% of the classifications are misclassified. So in this example, where we have 1,100 classifications for 100 collimators, this will average out to around, in theory, of course, 1 misclassification per collimator out of all the classifications required to align a collimator. So at the end of the day, all the collimators are indeed aligned. Okay, so hopefully that's clear. And now we can move on to the software architecture. So here we have the collimator. This is the actual hardware. And we move this hardware using software in C++. Now, when I say C++, I'm actually referring to FESA, which is a real-time control framework developed to basically implement equipment software for the LHC. So here we have a piece of software that controls directly the movement of the collimators. On top of this, we have another piece of software which implements the semi-automatic alignment, and this communicates directly with the software that controls the collimators. Now, the semi-automatic alignment sends the BLM signal and the collimator position to the application developed in Java in order to be able to monitor these signals. And from this display, the user and then was able to monitor these signals and must constantly oversee the position of each of the collimators, and based on this, control the collimator alignment by sending commands to the semi-automatic alignment. Now, this is the software before 2018. From 2018, I introduced a new piece of software, which is where the fully automatic alignment is implemented. Now, this can directly get the data, again, the BLM data and the collimator position from the semi-automatic alignment software. It will send the data required for the machine learning models that are implemented in Python using the scikit-learn, and this will send back the classification of the collimator, whether it's aligned or not. And based on this, the fully automatic alignment can then send commands to align the collimators automatically. Of course, we would still need to monitor the fully automatic alignment and the position and everything of the collimators, so everything is sent to the same application in Java for the display, and then the user can use this to monitor the alignment. Of course, this is a completely different experience now for the user, because the user only needs to monitor this and intervene in case of any issues with the alignment. Now, it's important to say that this software is readily available as of 2018, and it's available to use in the control center, and we actually used it to align all the collimators during 2018. And also, it's worth to mention this was the first machine learning application used for LHC operation. Okay, so now I can present some results. So we align collimators at the start of each year during the commissioning phase at all machine states. So if we take run 1, for example, which started in 2010, here we have the time taken to align the collimators. We have in blue the collimators showing the collimators to be aligned in B1, and in red the collimators to be aligned in B2. And here we can see that they're aligned at the same time in parallel. And then the yellow block refers to any reconfigurations of the collimator positions required throughout the year. So in total, in 2010, it required just under 80 hours to align all the collimators at different machine states. Over the years, we had a number of software and hardware upgrades. And for example, and then we moved to 2011, where, as I explained, the collimators were aligned with the semi-automatic alignment for the first time. And we can see that the time has improved. And then there was a further improvement in time when 12 Hertz data was available to align the collimators instead of the 1 Hertz data that was available back in 2010, 2011. And we can move on to run 2. In 2015 is when the beam position monitors were introduced for the first time, and these were embedded into the collimators that are mostly used for the reconfigurations throughout the year. So here we can see that this yellow block has begun to shrink. In 2016, 100 Hertz data, BLM data, was made available, so this further sped up the semi-automatic alignment, and we can see that the semi-automatic alignment sort of converged to just under 6 hours in 2017. Now in 2018, that is when we use the fully automatic alignment. So I can explain this in a bit more detail. So firstly, it's important to note that LHC beam tests are only possible a handful of times a year. Now, the first version that I developed of the fully automatic alignment was ready by commissioning 2018. And this is the first version because basically I explained before that they would align beam 1 and beam 2 collimators in parallel, whereas this first version was only able to align the collimators of the 2 beams sequentially. And as this was used during commissioning, it was used both for alignment at injection as well as alignment at stack top. So if we look at this plot here, at the start I explained how when we align a collimator, we have to align the reference collimator before and after the collimator. So here what I plotted is the position of all the reference collimators, which are 3 reference collimators per beam. So here, for example, we have the reference collimator of the horizontal plane in beam 2. We have the left jaw and the right jaw, and we can see that the jaws are moving closer and closer to the beam each time we align a different collimator. Once the beam 2 horizontal plane was ready, we moved on to the vertical plane, and same for the skew. And here we have the beam intensity. Here we can see that the intensity of beam 2 is decreasing as we slowly touch the beam with the jaws and slowly scrape it away. And once beam 2 was ready, we then moved on to beam 1. So again, beam 1 horizontal, beam 1 vertical, beam 1 skew, and the same, the beam intensity is decreasing in beam 1. So this is what I mean by first we aligned beam 2 and then right after we aligned beam 1. Now this was the first version of the fully automatic alignment. Later on in 2018, I developed a second version of the fully automatic alignment, and this restored the parallel alignment of the collimators. Now, at this point of the year, commissioning, of course, was already ready. So I had to get dedicated beam time to test the software, and I was able to use it as injection only by recreating sort of the commissioning environment. So now, if we look at the same diagram that I had before, here we can see that the collimators in the beam 1 horizontal plane are aligned in parallel with the collimators in the beam 2 horizontal plane. Likewise, for the vertical plane of the two beams, and then the skew. And we can see here the intensity of the two beams decreasing together. So now the question that remains is, how do we know that the fully automatic alignment has generated valid results? So at the start, I mentioned that the reason we align the collimators is to be able to calculate the beam center and the beam size at each of the collimators. So here what I'm showing is, for each collimator, we have the beam center, and these are the results obtained during commissioning 2017. In 2017, we were still using the semi-automatic alignment, which is the old software without machine learning. And this was already being used for the previous 6 years, from 2011 to 2017. So we know for a fact that this software generates valid results. Now, here I'm plotting the first results of the fully automatic alignment using the first version where the collimators were aligned sequentially. And we can see that the beam centers are consistent with the ones generated by the old software. Likewise, now I am plotting the results generated during the test with the fully automatic alignment that is able to align the collimators in the two beams in parallel. And finally, for comparison, I'm also plotting the results from the beam position monitors at the few collimators that actually have BPMs. And we can see that all of these centers are consistent. Likewise, I also plotted here the beam sizes at each of the collimators, and we can see these are consistent. So what does this tell us? That the beam centers and the beam sizes generated with the new software are consistent to those generated with the old software. And on top of this, the results that we got from the new software were actually the positions that we used for LHC operation all throughout 2018. Okay, so now that we've seen the results, we can go back to the timing. So here we have as I said, the time to align the collimators at over the years. I forgot to mention that this is the net time required to align the collimators without including any operational overhead. And if we look at 2018, which is the first version where the two beams were aligned sequentially, here we can see first beam 2 was aligned and then beam 1, as I explained. We can see that there was already, we saved 1 hour here to align the collimators. Now, as I explained, these are the times taken to align the collimators during commissioning. So we have the times at all the different mission states. Now, for the parallel alignment, this was only used at injection. So in order to be able to compare the times, I would need to remove all the times taken during the other machine states that were not at injection. So I will take those away, and now here we have the times required to align the collimators only during injection. And if we make this a bit bigger, now we can compare the time taken to align the collimators using the second version of the fully automatic alignment. And we can see here that it was able to align 79 collimators in 50 minutes without requiring any human intervention. And here again, we can see that beam 1 and beam 2 are back to being aligned in parallel. So that's pretty much it for this. Now, I would also like to take this opportunity to present some ongoing research on this topic. So the question that we have that remains is basically, can we align collimators faster? Now, I have a student, John Marco now, who is actually one of the attendees here. He is dedicating his master's thesis to try and answer this question. So to give an introduction, basically, I explained before how from the BLM losses, I was extracting the features, and based on these features, and then the machine learning was determined in real time whether a collimator is aligned or not. Now, from experience, we have converged on estimating that the time for the spike to decay is 4 seconds. So essentially what I'm saying here is that once 4 seconds have passed from the collimator stopping its movement, we will then apply the machine learning based on the features extracted here to determine whether a collimator is aligned or not. Now, what Gianmarco is doing is he performed some analysis using the mean lifetime and the half-life of the BLM signal. And we can see here, for example, in this case, that in order for the spike to fully decay, we don't need a full 4 seconds. So this is not always the case that we need 4 seconds that we need to wait 4 seconds before we can apply the machine learning. And what he's looking at is he's looking to apply LSTMs, where basically he's inputting the BLM signal to the LSTM, and he's outputting the probability that the losses form an alignment spike or not. And the reason for this is that the idea is to use this probability to sort of filter out the jaw alignments that need more time to decay, that need more decay time to be classified. So essentially what this means is that we're trying to determine in real time how much time we need for the spike to decay. And this way we would save more time when we're aligning the collimators automatically and not always wait the full 4 seconds before applying machine learning. Okay, so as a summary, we align collimators each year using a beam-based alignment. And I demonstrated that the alignment can be fully automated using machine learning. And in fact, this was used all throughout 2018. This new fully automatic software successfully decreased the alignment time by 70% from the previous software, which was used in 2017. And essentially, this created the foundations for introducing other alignment techniques, such as angular alignment, and also it created an environment for more detailed analysis on the topic. Finally, this fully automatic alignment will be used as the default alignment software for the startup of the LHC in 2022. Thank you for your attention.